All right. So last week we have considered the derivative of a complex function, and I have asked you to show that if a complex function is differentiable at the point, then it is continuous at the point, right? Okay. Now I will take another example. So consider a complex function, which is just the complex conjugate of C. All right, this function is not differentiable at any point Z in C. Okay. All right, so we compute the quotient. All right, so we compute the quotient. Okay, and this is quotient minus divided by delta Z. Okay, so here. And obviously now, for complex conjugate, the complex conjugate of a sum is equal to sum of complex conjugate. So this becomes to here, okay, for every delta Z. Okay, and okay, so if we express delta Z to be the real part delta X plus imaginary part I delta Y, then we know that this quotient is equal to this quotient. Okay, and if we take, so you can see that if we set delta Y to 0, okay, so if we approach okay, so now, so this is Z, right? And so if we go in this way to go to there, okay, or we go from here. So if we approach Z horizontally, that means that delta Y equals 0. Okay, so if we go this way, now then the ratio is 1. Okay, so all right. So now maybe I will see that. So limit delta Z goes to 0 of the ratio equal to limit delta X plus I delta Y goes to 0 of the ratio okay, and we can see that if we approach Z okay, horizontally, then the ratio, you see the ratio is equal to 1, right? And so the limit is 1. The other way is that if we approach x vertically, so okay, vertically, then then the ratio is -1. So it depends on how you approach z. You can see that the limit will be different. Okay, so that this function is not differentiable at any point. Okay, so this is the case, and this is the case here. Any questions? All right, now a complex function f of z is said to be analytic in a domain D if f of z is defined and differentiable at all points of D. Okay. Now, a function and a complex function okay, f of z is said to be analytic at a point z equal to z0 if f of z is analytic in a neighborhood of z0. Okay. Okay. Now, so as we know, a neighborhood of z0 is actually an open disk with center z sub 0, right? And the radius, certain radius r, right? So a neighborhood of z sub 0 is a domain. Okay, it's a special kind of domain because it is an open connected subset. Okay. So when we say a complex function is analytic at a point, we mean that it is defined on a neighborhood of z0, okay, and is differentiable at every point in this neighborhood of z0, okay. Okay, as we say here, right? Because we say, so this definition is a special case of the first one, right? Any questions? Now, a complex function okay, a complex function of z is called an entire function. Okay, if it is analytical in the whole complex plane. Okay, so an entire function is a function which is defined on the whole entire complex plane, and is differentiable at every point in the complex plane. Okay, so it's called entire function. Right. All right. And from our previous example in last Thursday, we consider polynomial functions, right? So every polynomial function f of z okay, is an entire function. Okay, so as you can prove, because that's a polynomial function defined on the whole complex plane, and it is differentiable at every point. Okay, so, and you can find its derivative, right? As we have computed last Thursday. So polynomial function, every polynomial function is an entire function. Okay. All right. And a rational function f of z, which is the ratio of gz and hz, where gz and hz are polynomial relatively prime polynomial functions relative prime means that they do not have a common factor, right, of degree greater than or equal to 1. They can have common factor which is constants, of course, right? So any non-zero constants are their common divisors. But when we define that two polynomials, relative prime means that they do not have a common factor of degree greater than or equal to 1, right? So that is we call relative prime. Okay, so that means that they don't have common factors, all right, of degree greater than or equal to 1. Okay. So, and h of z is not equal to 0. Okay, so the denominator cannot be 0, right? So a rational function, right? So the rational function can be expressed, all right, by a ratio of two polynomials. Okay. All right, and so a rational function actually is analytical, right? At all points in C, except, right? Except where that h of z is equal to 0. Okay, right. Because when you have z such that h of z is 0, then it's not defined actually at the Ross point. Okay, but whenever h of z is non-zero, then this function is analytic at Ross points. Okay, and as we know, every complex polynomial, all right, if the degree of the complex polynomial of h of z is n, then we have n zeros, right? N zeros, and they can be repeated, right? So at most, we have n distinct zeros. Okay. It is possible that h of z is a power of a linear factor. It's possible. Okay. In that case, you have only one 0, right? With multiplicity. Okay. So okay. So rational function that is easy to see that is analytical. Okay, at all points except at the point where the denominator is 0. Okay. Any questions? All right. So now we will move on to consider Cauchy-Riemann equation. All right, so first of all, we state a theorem. Okay, this theorem is called the Cauchy-Riemann equation. Okay, so let complex function, all right? And it's so u of xy, u of xy, it's real parts, and v of xy is imaginary part. Okay. Okay, be defined in a neighborhood of a point z0, which is equal to, right? So we consider a complex function, which this function is defined in a neighborhood of point z0, and it's differentiable. Okay. At z equal to z0. Okay. All right. So the premises is that this complex function is differentiable. Okay, at a certain point, z sub 0. Of course, that that is defining a neighborhood of such a point. Okay. In order to compute its derivative of f at z equal to z0. Okay. All right. Then at that point, okay, the first order partial derivative okay, of u and v exist, okay, and satisfy the Cauchy-Riemann equation that ux x0 0 is equal to vy x0, and the uy x0 y0 is equal to minus vx x0 y0. Okay, so these two, you can see, these two are first order partial differential equations. Okay, involving two functions u and v. Okay, and these two functions are just the real part and the imaginary part of the complex function. Okay, so Cauchy-Riemann equation is a consequence. It's a consequence of the differentiability of a complex function at a particular point. Okay, so there are consequences, and they are actually a system of first-order partial differential equations because it involved two functions of two variables, x and y. Okay, so they are systems, right? Because they are related to each other. Okay. Okay, so now we'll show all right, and hence, if f of z is analytic, okay, in a domain D, then first order partial derivatives of u and v, okay, exist, and satisfy the equation. All right, so satisfy the Cauchy-Riemann equations. Sorry. Okay. So satisfy the system. This is a system of first-order differential equations at all points, okay, of D. Any questions about the statements of this theorem? Okay, so it is only necessary to prove that differentiability of f at certain points implies that this system of first-order differential equation, okay, at a point x z0, okay. Okay, so let's see a proof. So now we have we have assumed that the derivative exists. Okay, so the premises of the theorem assume that the derivative, okay, at z equals z0 exists. Okay. All right, so let's see. So this is z, and this is z plus delta z, okay? And the derivative, the existence of derivative says that no matter how z plus z delta z approach to z, it can be going this way, right? Or can be this way. Okay. No matter how it approaches to z, okay, the limit always exists. Okay. Now we will take two particular paths to go to z. Okay. The path one is here. Okay. So this is path one. And the other path is here. Okay, so this is path two. This, right? So we will select two particular paths, okay, to approach to z. All right. Okay, so now, so we let, so of course, delta z is equal to delta x plus I delta y, and z0 is x0 plus I y0. Okay, so that, and so that z0 plus delta z is equal to x0 plus delta x plus y, y0 plus delta y. Okay. All right, so with that, now the ratio okay, so now we can compute the ratio. The ratio becomes to, so now the okay, and the real part, well, so let me write here. So f of 0 plus delta, which is v of x0 plus delta x, y0 plus delta y, plus I, this is u, right? And the v x0 plus delta x, y0 plus delta y. Okay, right? And the f of z0, which is u of x0, y0 plus I v x0, y0. Okay? All right, so the difference, so when we see the difference, all right, in the numerator, you see the difference that the real parts comes to be u of x0 plus delta x, y0 plus delta y, okay, minus u x0, y0. So this is the real part. And then the imaginary part is vx0 plus delta x, y0 plus delta y, minus vx0 and y0. So this is the numerator, and the denominator x delta x plus I y. Okay, so you can see the ratio here. Now, by pass one, okay, by pass one, right? So by pass one, you can see that so that the delta y goes to 0 first, right? So delta y goes to 0 first, right? And then delta x go to 0. Okay. All right, and so f prime z, okay, 0 becomes to delta x go to 0, and the delta y goes 0 first, and then delta x go to 0 at the second. See here. Okay. Now, for when delta y goes to 0 first, then you can see. All right. So look at the the numerator. All right. So delta y goes to 0 first, so that now you have that's u of x0 plus delta x and y0 here, okay, minus u of x0, y0. So this is the real part. And for the imaginary part, we have v of x0 plus delta x and y0 minus v x0 and y0, okay? And for the denominator, this is goes to delta x only, okay? Because that when you take the limit for delta y goes to 0, we have a limit for the numerator and a limit for the denominator, okay? Because the denominator accepts a linear function of delta y. So delta y goes to 0, this is go to 0, and you have delta x here. All right. Remember, delta x goes to 0 means that delta x is always non-zero, okay? But approach to 0, okay? This is the definition of limit as a convention. And this function, all right, u goes to this one because of things u and v are continuous at okay, because u and v is differentiable at z0, and I have asked you to show that if a complex function f is differentiable at a point z sub 0, then it is continuous at z sub 0. And if a function is a complex function is continuous at z sub 0, then its real part and the imaginary part also continuous at at the point x0, y0. Okay, so that we have used this factor, because this factor is a consequence that the complex function f is differentiable. Okay. Okay, right now the ratio, because this always exists, right? So when delta x goes to 0, the real part, the ratio must exist, so that limit all right, so which means that this limit exists, also this limit exists. But the limit of this ratio is just the partial derivative of u with respect to x, right? Okay. Right? Because they are equal to this one. So which shows that the first order partial derivative of u and v with respect to x exists. Okay. And we have f prime z0 is equal to ux x0 at and we have okay, so we have the result that the derivative of the complex function f at the point z sub 0 is equal to that this expression where the real part is just the first order partial derivative of u, okay, with respect to x at the point x0, y0, and the imaginary part is just the first order partial derivative of v, okay, with respect to x and at the point x0, y0. Okay, so this is when we approach to z by using path 1. Okay, and similarly by path 2. So similarly, by path 2. So path 2 means that we let delta x goes to 0 first. Okay, and delta y goes to 0. Okay, so that f of f prime z0 is equal to limit delta y goes to 0, and here is minus u x0 delta y plus limit delta y goes to 0, I delta y, and the v x0, y0 plus delta y minus v x0, y0. Okay? Because when we take delta x go to 0 first, so that delta x go to 0, and when delta x goes to 0, the denominator becomes to I delta y here. Okay, so we have I delta y here. All right, and so these two limits exist, right? So which shows that the first order partial derivative of u and v with respect to y exist at the point x0 and y0, and we know that f prime z0 is equal to minus I, okay, and uy at x0 and y0. Oh, plus I here, okay. So minus I and I cancel, so we have v y x0. Okay. All right. So now we have vy x0 y0 and I of minus uy x0 y0. Okay. Okay, and compare these two. So we find that the real part will be equal, right? So that ux is equal to vy, and the imaginary part vx x0 y0 is equal to minus uy x0. Okay. Okay, so which are just the Cauchy-Riemann equations. Okay, so we have that. Okay. Okay. So so the differentiability of a complex function, right, at the point z sub 0 implies that the real part and imaginary part has first order partial derivatives. Okay, at the point x0, y0. Okay, and these four first order partial derivatives satisfy the Cauchy-Riemann equations. Any questions? And of course, then we have a converse theorem. If two real valued continuous function uxy and vxy of two real variables x and y, okay, have continuous first order partial derivatives. Okay, first derivatives. Ux, Uy, Vx, Vy that satisfy the Cauchy-Riemann equations in 13.1 in some domain D. Then the complex function defined by these two real valued function. Okay, so now the complex function is analytic in D. Okay, in D. So here, the statement of the theorem says that first of all, we have two real value continuous functions, u and v, right? So they are continuous in a domain, right? And these two functions has continuous first order partial derivatives, okay, in the domain D, and satisfy the Cauchy-Riemann equations, right? So everything. Then the complex function is analytic in D. All right. So now we compare these two. So we say in here, right? If Fz is analytic in a domain D, then the first order partial derivative u and v exist and satisfy, okay, the Cauchy-Riemann equations. And as we know, if f of z is analytical in a domain D, then the complex function is continuous, right, at every point in a domain D. And so that its real parts and imaginary parts are continuous function at every point in the domain D. Okay. All right. And also, the first order partial derivatives exist. And later on, we will show furthermore that that their first order partial derivatives are also continuous. Okay. Later on in chapter 14, we will say that. So the derivative we will show the derivative of f is also analytical. Okay. All right. So this is our main job, right? So if f of z is analytical in a domain, okay, so of course it has derivative, right? F prime z. And in the next chapter, we will show its derivative is also analytical in the same domain D. Okay? So it has second derivative. And by induction, if any complex function is analytic in a domain, then it has nth derivative for all n. Okay? And we will show that. Okay? So this is our main job. All right. So that if the derivative of f of z is analytic, which means that the first order partial derivative has also partial derivatives. Okay, so that they must be continuous. All right. Okay, and so this theorem, these two theorems actually, this is a converse, right? So it's an if and only if condition. Okay, it's an if and only if condition indeed. Okay, but at this moment, and it is a very good theorem to justify whether a complex function, to be analytical in a domain or not, because you just verify its real part and imaginary part to see if they are continuous functions, right? And in a domain, and they have continuous first order partial derivatives. Okay, so these conditions are quite easy to be justified. Okay, to be justified. So once we know this fact, then f of z, all right, would be analytic in the domain D. Okay, right. So this is a very good theorem, and the proof actually is not difficult, right? Very similar to what we have done, but applied other mathematical theorem like the mean value theorem. So the textbook. So please see page A78 in appendix 4 of the textbook. Okay. Right. So I ask you to see it. Okay. Right. So it's required mean value theorem in multivariable functions. So okay. So that I ask you to look at a proof. Okay. But at least you should know how to apply this theorem to justify whether a complex function is analytic or not. Okay, one way is to show the existence of its derivative, right, directly, as we have done last week. Okay, for polynomials or monomials. Okay, and so this is a direct way. The other way is to apply this theorem, right, to work on its imaginary part, its real part, and the imaginary part first. Okay, so this is another way to have that. Okay, any questions? Okay. If not, then we have a break up to 2:20. All right. Now we want to use the Riemann-Cauchy equation to show a fact. Okay. If f of z is analytic in a domain D such that this analytic function has constant modulus. Okay, such that its absolute value is a constant. Then f of z is equal to a constant in D. Okay. All right, so now we show this. F of z is equal to u of xy plus I v of xy, okay, which is analytic in the domain D, and such that we know that u square xy plus v square is k square. It's a constant. Okay, right? So the square of the magnitude is just equal to this sum of squares, right? So we know that. And from this equation, okay, right, if we take the partial derivative with respect to x, so now we have ux, okay, plus vx is equal to 0. Right? So we take the first order partial derivative with respect to x, we get this one. And if we take the first order partial derivative with respect to y, then we have uy plus vy equal to 0, right? So we have these two partial differential equations here. Okay. Now we apply the Riemann-Cauchy, the Cauchy-Riemann equations. So we know v of x is actually equal to minus uy. So this is ux minus v uy equal to 0. Okay, and for this one we have uy plus v ux equal to 0. Okay, because vy is equal to ux. Okay, this is from the from the Cauchy-Riemann equations. Okay. So here we know ux is equal to vy, and vx is equal to minus uy. Okay, so this is the Riemann, the Cauchy-Riemann equations here. Okay, so we have this too. Okay, so now we have a system of homogeneous first order partial derivative, first order PDEs, right? And now, so we can cancel uy, okay, by multiplying the first equation with u, okay, and multiplying v, right? So v u uy plus v square ux equals to 0. Okay? And then we add these two together. So if we add them, okay, we find that we have u square plus v square of ux equal to 0. Okay? And this is a constant, right? K square. So now if u square plus v square equal to k square is 0, okay? So if this is 0, okay, then u is 0 and the v is 0, which implies that f of z is 0, a constant already, right? So if u imaginary part and the real part and imaginary parts are 0 functions, then the complex function itself is 0 function, which is of course is a constant function. So c is 0. Okay. So now if u square plus v square equal to k square is greater than 0, right? So this is not 0, right? And so this is ux is equal to 0. Okay, so we have shown ux is 0. Okay, the other way is go to the other direction. So we cancel uy, right? But to cancel ux, so the other way is here. To cancel ux, we multiply vu ux, so minus v square uy equal to 0. So we multiply minus v to the first equation and multiply u okay, here, and we add them together. Okay, so the result becomes to u square plus v square times uy equal to 0. Okay, is that okay? And so if this is the case, then this and uy equal to 0. Okay. Now by Cauchy equation, and then also vy equal to 0 and the vx equal to 0. Okay? This is from the Cauchy-Riemann equations, right? So if ux is 0, then vy is 0. Vy is 0, right? And when uy is 0, then vx is 0. Okay, so all the partial derivatives with order values are zeros. Okay, so that u is a constant, and v a constant too. So, okay, so this implies that fz is a constant, and we have done. Okay. So this is an application of Cauchy-Riemann equations Okay, so whenever we have an analytic function in a domain D such that this analytic function has constant modulus, okay, means that its magnitude is equal to a constant, then this analytic function must be a constant function. Okay. Any questions? All right. Now, so now with polar form, okay, with polar form, Z can be write as, okay, so Z can be, now this time, instead of X and Y, we use R and the theta, right? So this is the polar form. And so that Fz can be written as U tilde R theta plus I with tilde R theta, where U tilde R theta is equal to U X R theta Y R theta, and the V tilde R theta is equal to the V X R theta Y R theta. Okay, right? So we have coordinate transformation, and okay. And the Cauchy-Riemann equation in polar coordinate systems are U tilde R is equal to 1 over R V tilde theta, and V tilde R is equal to 1 minus R U theta. Okay? So now the Cauchy-Riemann equation in polar coordinate system becomes these systems here. Okay, becomes these systems. Okay, and so please see. So this will be an exercise problem. So please see problem 1 in section 13.4. Okay, so that you will be asked to show this relationship. Okay. All right, now we shall prove. I have mentioned before, we shall prove that the derivative f prime z of an analytic function f of z in a domain D is also analytic in D. in chapter 14. Okay, so in next chapter, we will show that the derivative f prime z of an analytic function is also analytical indeed. Right? And because f prime z is analytical, so its derivative f double prime z is also analytical. Right? So by induction, the nth derivative of an analytic function is also analytical. Okay. Right? Right. And this shows that the real and imaginary part u x y and v x y has partial derivatives of any order. Okay? So it is very powerful. If f of z is analytical in a domain, then its real part and imaginary parts has a partial derivative of any order, right? Any order you can take. Okay. So this is very well behaved. Okay. And so now we can have the next theorem. Okay. So if f of z is analytical in a domain D, then both u and v satisfy Laplace equation. Okay, so Laplacian uxx plus uyy is equal to 0, and Laplacian v is also equal to 0. Okay, indeed. Okay. So that the real parts and imaginary parts of an analytic functions in a domain D will satisfy the process equations. Okay, so that any solutions of the process equations, okay, so they can be used to serve as real part and imaginary parts. Okay, if they satisfy the Cauchy-Riemann equations. Okay, all right. So analytic functions. It's the theory of analytic functions is closely related to the harmonic analysis. Means that they are real and imaginary parts satisfy Laplace equations. Okay. So they satisfy in D, and have continuous second order partial derivatives. of course, they have. Okay, and this second order partial derivatives are also, they are all continuous. So actually, the existence of continuous second order partial derivatives is because the remark I stated here, that that the derivative of any analytic function is also an analytic. So that the real and imaginary parts u and v has partial derivative of any order, and because of that, any partial derivatives should be continuous. Okay, should be continuous. All right, so that's why we have, so u and v should have continuous second order partial derivative. Actually, they have a continuous any order partial derivatives. Okay, any order partial derivatives, and they satisfy Laplace equation. It is because you can apply the Cauchy-Riemann equations to show that. All right, so let me give a quick proof here. Okay, so from Cauchy-Riemann equations, so we have ux equal to vy, and vx equal to minus uy in D. Right? So from here, so we have, okay. So now we further, because we know that u and v has partial derivative of any order, okay, and that this value are all continuous. All right. So when we take partial derivative again, right, with respect to x, so we have uxx equal to vyx here. Okay. And here we take partial derivative with respect to y. Right. So vxy equal to minus uyy here. Okay. And from these two, because that the partial derivative are all continuous, so vyx and equal to vxy, right? So you can change the order of partial derivative, okay? Because they are continuous. So that's the, okay? So this is implies that uxx equal to minus uyy, all right? Since vyx is equal to vxy, okay? By continuity. Okay. So we have, and so this is the Laplace equation. And similarly, we take the partial derivative with respect to y, so vyy here. Okay, and we take the partial derivative with respect to x here. So this is implies that vyy equal to uxy, and this is uyx, and this is minus vxx. Okay. By the continuity of vxy, uxy, and uyx. Okay, so they are equal, and so vxx plus VYY equals 0 in D2. Okay. So both V and both U and V satisfy Laplace equations. Okay, so solutions of Laplace equation having continuous second order partial derivatives are called harmonic functions. Okay. So harmonic functions are functions which are solutions of Laplace equation and have continuous second order partial derivatives. Okay? So they are called harmonic functions. Now, if two harmonic functions U and V satisfy the Cauchy-Riemann equations, in a domain okay, then they are real and imaginary parts of an analytic function. F in D. Okay? By theorem 13.4.2. Okay? So from this theorem, we know that if we have two harmonic functions now satisfying the Cauchy-Riemann equations in a domain D, then they are real and imaginary parts of an analytic function in D. Okay, from that. In this case, okay, V is said to be a harmonic conjugate function of U in D. Okay, so in this case we can all right, so we take an example here. Okay. All right, so verify that the uxy x squared minus y squared minus y is harmonic in C, right, in the whole convex plane, and find a harmonic. Oh, sorry. HAR, a harmonic conjugate. Conjugate function V of U. Right? Okay, so we first verify that it's harmonic. To verify that it's harmonic, you should justify that it's a solution of Laplace equation, right? So first of all, verification. All right, so we take Ux, right? So Ux is 2x, right? And Uxx is equal to 2. Okay? Okay. Now, under Uy is minus 2y minus 1. And Uyy equal to minus 2. So that's Uxx plus Uyy equal to 2 plus minus 2 is 0. So you can see, all right? So, and also you can see that that Uxy, so Uxy is equal to 0, okay? So now we have 3 so the 4 second order partial derivatives of U are all continuous, right? They are all continuous. So that is a, right? So that U is a harmonic function. Okay, so the verification is okay now, right? So this function is a harmonic function because that it satisfies Laplace equations, and the 4 second order partial derivatives are continuous. Okay, we just write down the formula here. And the second finding harmonic conjugate, right? V of U. All right, so we have to find that. Now, to be a harmonic conjugate, so they satisfy the Cauchy-Riemann equations, right? To be harmonic conjugate by definition. Okay, so they satisfy the Riemann-Cauchy equations, Cauchy-Riemann equations. All right, so now Vx should be equal to minus Uy, okay, and minus Uy is 2y plus 1. Okay. The other is Vy is equal to Ux, and which is 2 times x. Okay. Now we integrate. So V xy with this one by integration, okay, of Vx dx. So now we have 2xy, okay, 2xy, well, okay, so 2xy plus plus x plus a constant. Right? So anyway, and the hy and the x of y here. Okay. From there. All right, and so this is implies that Vy, right? So Vy, this is equal to 2x plus h prime y, and which is equal to 2x. Okay. So this is implies h prime y. It's 0, which implies that the hy is a constant c. A constant. Okay. All right. So now, Vxy, now we know it's 2xy plus x plus a constant. Okay. And you can see that. Of course, it satisfies it's a harmonic function. The reason is from the Riemann, the Cauchy-Riemann equations. So this V must be a solution of the Laplace equation, of course, right? And it has continuous second-order partial derivatives. Okay, and we can see the convex function. So the convex function, so this is x squared minus y squared minus y plus I 2xy plus x plus a constant. And it is very interesting to know this is, okay? And you can see it's a polynomial function. Okay? So if you construct the convex function with u and v, you find this is a polynomial function. Okay? So it's a polynomial function of degree 2. Okay, very interesting. Okay, so any questions? Now, because the exponential function is very important, so I now decided to explain the creation of exponential function. Okay. We want to create an a complex version of a real of the real exponential function. Ex. Okay, so want to create, right? By requiring the following three properties. First of all, E of x, z, the new function, so it's an extension, right? So we want to have a complex version, right? Means that it's an extension of the real exponential function. So we want if z is equal to x, okay? So if z, this complex number z, is a real number x, then they should be equal, because this is an extension, okay? The second, we want Ez is analytic, okay, in C. Means that Ez is an entire function. Why? Because, as we know, the real exponential function is well behaved. They have a derivative of any order, right? And as you know, the derivative of E of x is also itself, right? Do you know that? Okay. So you have, right? So that they have it's differential. At least exponential function is differentiable at every real point x. So we require that Ez is analytical, means that Ez, this complex function, should be differentiable at every point in the complex plane. And the third one, that's of course, we want the derivative, right, of Ez should be itself. Because the derivative, as we know, is itself, right, in the real world. Okay, so we want to create a complex version of the real exponential function. So satisfy these three properties. And they are reasonable, right? To have functions having these three properties. Okay, and now we will show with these three properties, the theorem all right, so with properties 1, 2, 3, the complex exponential function Ez equal to Ex times cosine y plus I sine y. For z equal to x in C. Okay, so we will show that with these three properties, the exponential function, okay, has the real part, which is Ex cosine y, and the imaginary part, which is Ex sine y. Okay, all right. So here is the proof. Okay, so I'll give you show proof. Right, by 1. Okay, so all right, so we know that. Okay, so we let Ez to be Uxy plus I Vxy. Okay, because any complex function has real part and imaginary part here. Okay? All right, and by 1, we know that Ux0, so Ux0 is equal to Ex, and x0 is equal to 0, okay? If you think, okay, so okay. Okay, Ex is equal to U equal to U x0 plus I V x0, okay? And we know this is Ex. This is implies that Ux0 is equal to Ex, and the Vx0 is equal to 0, okay, for all x in R. Okay, this is from property number 1. Okay. Now by 2, because that it is analytical, right? So we know Ux is equal to Vy, and Uy is equal to minus Vx, okay, in the plane, okay, in the whole plane here. Okay, and by 3, we know that easy prime, right? We know easy prime is equal to Ux plus I Vx, okay? From our derivation, in the proof of Cauchy-Riemann equation, we know the derivative of a complex function is equal to Ux plus I Vx, right? Vx. And as we know, this is equal to Ez, so which is Eu and IV, okay? So now it implies that we have Ux equal to U and Vx equal to V. Okay? So we have two first order partial differential equations. That's okay? This is from the third property here. Okay. And so we can integrate, we know, so we know that there must be exponential functions. So U is equal to AY and the exponential function of X. And also V is also BY, exponential of X. Okay, is that okay? Because this is first order partial differential equation. So they are exponential function, but the constant here depends on Y, of course. Okay. And from the initial condition here, see here, so we know that so they are with A 0, all right, A0 equal to 1, okay, because that here, so this goes to here, and this goes to here, the B0 is 0. Okay? So these two provide some boundary special values, right? So A0 is 1. Okay? A0 when y equal to 0. So you get A0 is 1. And from here, you know B0 is 0. Okay. Okay. Now A and B can be obtained in the following way. So also another way is that okay, another way is, so this is also equal to, oh, we know this is Vy plus I minus Uy. Okay, so now we see Vy is equal to U, and Uy is equal to minus V. Okay. Okay. You know the derivative has, this is by using the partial derivative with respect to x. This is with respect to y. This is obtained from doing the past one, right? Remember when we proof the Cauchy-Riemann equations. Okay, we get two intermediate results, right? This is 2, and so we have that. Okay, and so that we compare. So when we do that, now we go to done. Okay, we have that. So when we do this one, so Vy here. So Vy becomes to B prime y, and the Ex, and which is equal to U, right? So it's Ay and Ex. Now this one for Uy, so this is A prime Uy is equal to A prime y, Ex, okay, equal to minus V, and minus V is minus By, and Ex. Okay. Is that okay? We do the substitution into here to get these two equations. So here we know B prime y equal to Ay, and from here A prime y equal to minus By. Okay. Right. And combine them together. Right. We will see that B double prime plus B equal to 0. A double prime plus A equal to 0. Now, so we have what? We have harmonic equations. Right? This is the second order ODE, and we know how to solve them, right? So now the solution is that AY becomes to A1 cosine Y plus A2 sine Y. And the BY, it's B1 cosine Y plus B2 sine Y. Now we apply special cases here. So now with B0 equal to 0, okay? So B0 is 0, right? So B0 give us B1, okay? So B1 is 0. B1 is 0 here. Okay, so this is implies that By is equal to B2 sine Y. Okay? Now, AY is equal to B prime Y, right? AY is equal to B prime Y. So this gives us B2 cosine Y. Okay? And with A1, A0 equal to 1, this implies that B2 is equal to 1. Okay. So B2 equal to 1, right? So finally, by is equal to sine y. And ay, which is b prime y, become to cosine y. Okay. Right? And so when we determine A and B already, and so the final result is that so we get u xy becomes to ex cosine y, and the vxy becomes to ex sine y. So finally, ez is equal to ex cosine y plus I sine y. And then we have done. Okay. So from these three properties, very simple property and reasonable properties, the complex version of the real exponential function we call the complex exponential function should be this function. Okay? So there is no other possibilities. Okay. All right. This must be these functions. So you can see, again, the proof is also the application of the Cauchy-Riemann equations. So Cauchy-Riemann equation is very important, very fundamental in complex analysis. Okay. All right. So I stop here.